so maybe I should ask you that introduction. Okay, so these are the papers that I want to talk about. My work is done with Max Metlitsky, and there's a parallel paper by Chongwang and Senthil, and you can kind of see the numbers. So we ended up completely independently getting to the same conclusion around the same time, and then we posted the papers together. And this is probably for high energy theorists, probably this is the reference you want to read. So let me show you a picture of Max. This is Max Metlitsky, who's... I just lost my punchline.
You lost your punchline there.
Yes. So he's called the Witten of condensed matter. So look at the hairstyle. But he's also very, very brilliant, and he's also worked on some topics that are similar to what Witten has worked on. Okay, so I'm going to tell you about a new kind of particle-vortex duality, and this applies to Dirac fermions in 2+1 dimensions, and we'll see that it's related to physics in 3+1 dimensions, and there we'll do this electric-magnetic duality on topological insulators. So this title is sort of puts together pretty much everything I've ever worked on in my life. So it's been very exciting this work, and
where's entanglement? Okay,
yes, okay, that's the one thing. But yeah, maybe there's some scope for that. Let's talk about it. So also, there's going to be some very nice, theoretical physics, but probably what's most amazing is that it makes an experimental prediction, and I think this is a prediction that experimentalists can go and look at, tomorrow if they want. And it's also related to some very nice work by Damson, which I don't have the reference, where he asked the question whether composite fermions are Dirac particles. Okay, so we'll see that, and that's where it really connects to experiments in the quantum Hall effect, and that's why I'm here at this conference. Okay, so let me start with what the conjecture is and how much of the conjecture we can prove, that's I'm going to work in 2+1 dimensions. So on one side we have a single Dirac fermion. So we have a Lagrangian, that is some electron. Let me call this the electron. Okay, so I have a global U1. And forget for a moment that electrons are actually coupled to an electromagnetic field. At least in condensed matter applications, the speed of light is so large that we can sort of forget about that to begin with, and let's just think of a non-interacting fermion. It has a global symmetry, and we're going to work in 2+1D, where this psi is a two-component object, and these gamma matrices are some Pauli matrices essentially, some sort of Pauli matrices. So that's the theory on the left-hand side. And the claim is that it is dual in a certain sense to the following theory. I'll call these, again in terms of fermions, I'll call them composite fermions. You'll see why in a minute. So again, some two-component fermions. Okay, but the crucial difference over here is that these fermions are coupled to a gauge field. Here, U1 gauge field, and so there's also a Maxwell term. I should write down. Okay, so we'll talk a little bit about what exactly we mean by this duality, but in some sense, this is really just QED3. Okay. Which is being proposed to be dual to a single Dirac fermion. Okay, so you can ask where does the global U1, how is the global U1 identified? So let me just put in external electromagnetic field just to keep track of the charge density. So it turns out that the charge density of the electrons is captured by the flux density of this emergent electromagnetic field. Okay, so there will be a coupling. And there's a normalization over here, which is kind of important. 2 units of electromagnetic flux of little a will be 1 electrical charge. Okay, so over here, the charge density of electrons n will be identified with the magnetic field divided by 4 pi.
What about the composite fermion side? The charge, are there no charged particles under the ordinary charge of the composite? Are those confined? So I'm asking, what about the U1, your normal U1 charge on the composite fermion side?
Wait, you're having this global U1 charge?
No, the other side.
There's the electric charge here.
The gate charge.
Right.
Here.
Okay. So what is the gate charge on this side? Okay, so these, so another way of asking is what are the composite fermions, right? Those are the gate charged objects. So these turn out to be vortices of this electronic field.
So there are 2 conserved currents on each side? But you say that one is just gauge, so but still
Yeah.
there are 2 conserved quantities?
So over here there is a global U1, so there's of course the global U1 charge.
Yes.
And there is a topological density, if you like, which is the density of vortices, which is conserved.
Yes.
But the vortices over here, they're also point objects. In 2+1 dimensions, they are lines, so they are point particles in 2D. So if you write down an effective theory for vortices, which is similar to the duality for bosons, if I write down a theory for vortices, we'll talk about the statistics, but the vortices will interact via long-range interactions. But the usual argument is that a vortex sets up these currents and they cost energy. So when you run on a theory for the vortices, they always come with this gauge field attached, which gives you the long-range interactions and the fact that they are non-local objects in this theory.
So just to understand, here the A external was just a probe.
Yeah.
But to begin with, you just had this theory of a free fermion.
Yes.
So what are the vortices in that theory? Just to
Global.
but even that, for a simple fermionic theory?
Yeah, you can have vortices in the fermionic theory, yeah.
This is when you condensate side by side?
Actually, you don't need that, but if you like, you can do that. So what you can imagine that these fermions pair, form a superfluid and condense.
Okay.
And now you can examine the vortices in that superfluid.
Uh-huh.
And the unit vortex is a half vortex now, because you have a plate condensate.
Okay.
So the unit vortex is a pi vortex. Then there is a 2 pi vortex, and then there is a 4 pi vortex. And if you examine what are the properties of these vortices, when you start with such a theory, you'll find that the 4 pi vortex is actually a fermion. Which is
Ashvin, to make them condense, you need something else. You need some kind of an interaction. Free fermions are not condense, right? So the theory as defined is not quite complete.
Okay. So there's additional, sorry, just one there's additional interaction, see, and that causes the fermions to then condense and gives rise to vortices.
That's a way of thinking.
So that's
yeah. You don't need to do that if you don't want to. So if you ask me, let's say I give you a wave function, right? I give you a wave function in terms of the electron coordinates. How do you put a vortex into that wave function? Right? So one way to do it, at least on the quantum Hall effect, what you do is that you can pick a particular position, let's say Z, and you have all of these other electrons at various positions Zi. And you can think of the operator, which is Zi minus Z, right, acting on the wave function. So actually, let me just do this. So these are the coordinates of all of the electrons. So this would induce a vortex into the wave function. So the operator that does this is the actually this composite fermion it will turn out is actually the square of this. It's a double vortex. That's this normalization over here, 2 flux quanta.
Somehow this is not obviously related to this other way of thinking that you have a superfluid of group of pairs and then you have a vortex and that, but they are the same.
So this is the strength 4 vortex in that sort of world.
I see.
Yeah, because every charge over here, every electron will see 4 pi phase as it goes around this vortex, which is like a 4-4 vortex of there.
Can I ask a question in a slightly different way? Usually I think of a vortex as an order parameter winding, and here it's something in the wave function winding. But
yeah, that's
they're
right.
equivalent.
They are equivalent, yeah. You don't need an ordered state to talk about a vortex. So maybe one thing that would be useful to do is to go back to the boson vortex duality and see what we mean there. Because you can also describe the disordered phase where there's no order parameter in terms of vortices. It's a condensate of vortices, the many vortices. The ordered phase is easy because then you can just put in one vortex.
That I'm happy with. It's more the idea of thinking of vortices as windings and wave functions. I guess as high energy physics we never think about wave functions. So
Okay, yeah, that's just how because this is very explicit. So if you like, one thing you could do is you could imagine gauging this this potential, vector potential.
Yeah.
And then this is just the monopole insertion operator, which would put in a flux of not 2 pi but 4 pi. So it's the double monopole insertion operator.
Okay.
And vice versa as well. So if you ask if the density of electrons is the magnetic flux density, what is the operator that inserts an electron? Well, it should insert 4 pi units of flux. So this is the double monopole. So there's a double monopole operator that represents this electron insertion. So we'll see later that in the appropriate theory, when we do this electric magnetic duality, the double monopole will be fermionic and have all the properties of the electron.
Yeah, maybe this would help them. It's actually very physical. So you have this two-dimensional electron gas, you have magnetic field, think of them as flux lines, that's the external, and you want to get rid of all these flux lines in some smooth adiabatic manner. And one way of doing it is to go into that picture.
Right, yeah.
And then you have just a gauge field there.
Yeah.
This is how this picture arose actually. From this very physical way of thinking.
Yeah.
What do you have to do to get rid of that?
So actually, this is a zero magnetic field, what I'm describing. This is the. But what we do is, so how are we going to try to prove this? Right? One way is.
Sorry, just one more question. These vortices on the left-hand side or the charged particles on the right-hand side, do they carry finite energy? So one of them carry finite. Is it a finite energy state in your theory?
If I put in one of these,
Yes.
so you'll not tell me in which phase we're talking about. For energy, you have to tell me what the Hamiltonian is, what is the ground state, and then you make an extension. Right?
Okay, but free fermion, normally we think of there's no issue of phase, we have a free fermion.
Right.
So in the free fermion, if you want to put in this vortex, would it cost a finite amount of energy or some logarithmically divergent or something?
It'll be, it'll be logarithmically divergent.
Okay, or is it divergent?
It'll be, yeah. So it's, if you like, it's in this plasma. Suppose let's say this QED3 is actually a stable theory.
Right. In its ground state.
In its ground, it's some stable theory. And now what you want to do is you want to insert
A single charged particle. It looks like it has a log. It looks like it has an IR divergence in its energy.
yeah,
Right?
some IR level. Yeah.
So these are not states in it. So in some sense, there's only one conserved current on both sides.
There's only one physical.
One thing that you have charged states.
Right. Yeah. So this is, if you like, it's something fictitious. So it's something. It's topological, right? It's a topological density. Just like with regular vortices.
So you said if you gauge the thing on the left, then the 4 pi monopoles of the double monopoles of the gauge field on the left are the composite fermions on the right.
Yes. See, if you gauge this A, then these have short-range interactions.
Right.
Right? They become like physical particles.
You're basically interchanging the two sides.
Yeah.
But then, yeah.
Okay, so the way we'll try to make sense of this is we'll deform these theories and we'll show that they agree. Okay, that's of course not a proof, but that gives you some confidence that maybe the strongest statement is true. And then, if you have time, we'll do this electric magnetic duality and show that these things have the same. Every phase of this theory can be represented by some with some parameters over here, you can represent that phase with this other equivalent theory, just like with boson vortex duality. Okay, and at some point maybe we'll remind you about the boson vortex duality. There's one more thing that's important that has to be mentioned, which is what happens to symmetries. Because we're going to pay a lot of attention to time reversal symmetry. So topological insulators are only sharply defined when you have time reversal. Okay, so for example, on this side, if I think of doing time reversal symmetry, I can exchange these. Okay, so there's some anti-unitary operator. So anti-unitary, so I will go to minus I, and I'll think of these fermions as transforming in some way under this time reversal symmetry. On this side, you can ask what does that symmetry correspond to? And as very standard in these particle-vortex dualities, this will actually correspond again to anti-unitary, but it will be particle. It will behave like particle hole. It's the same symmetry, of course, but it will behave like particle hole. So psi will go to psi dash under this transformation. Again, I will go to minus I. Okay, so this is the idea that if I give you a fluid, you do time reversal on that, the particle stays the particle, but a vortex will become an anti-vortex under time reversal. So that psi goes to psi dash.
Sorry, what was the psi CF goes to epsilon?
Sorry, epsilon is like some matrix.
Oh, I see.
And such that if you act on it twice, you'll get minus 1, which you cannot gauge away. That's t squared and minus 1. Okay, so
I would have expected the opposite. If that's the surface state of a topological insulator on the left side, shouldn't time just act as I sigma y?
Okay, I can switch things around a little bit. It turns out this is some class A3, if you like.
Okay.
I want this to be a particle hole because eventually I'll make an application to the quantum Hall effect. This would be the lowest standard level of the quantum Hall effect, and then this would be topological insulator.
So you could in principle consider both kinds of.
You could do both, yeah. So let me do, you can flip the two around also. Maybe I'll do one or the other. Let's see how that. Okay, so. So in okay, so one question that was
sorry about doing both. So that means there are two different anti-unitary symmetries that exist.
Actually, I only really need one, but I could choose either one. Like I could choose this to be time reversal and that to be on that side be particle hole.
But both will be anti-unitary.
Both are they're always anti because that's like what the operator is, right?
Right.
It doesn't matter which variable you look at; it's just anti-unitary. And then the question is, how does it act on the fermion operators? In one case, it makes the fermion and the anti-fermion alone. The side doesn't care.
What about squaring to 1 versus minus 1? They both, does that change when you do this? Or?
No, that depends on which operator you're looking at.
Alright. Yeah.
If you look at these composite fermion operators, t squared will square to minus 1 to the number of composite fermions. Here, there's no such meaning because you're changing the charge.
The state.
Yeah.
There is just as a side, there is a standard time reversal operator in the free fermion theory, which is different from what you define on this side.
Either this side, what about that side?
That's the standard one.
That's the standard one, yeah. For finite theory.
That
This is in standard notation, this is C times T, charge conjugation times time reversal. So together it's an anti-unitary symmetry. Okay, so let me kind of compare this to boson vortex duality because that's something that everyone knows. Very quickly, let me remind you of boson vortex duality. And then you'll see that why do we believe boson vortex duality will so here what we have is on this side we'll have some boson field, the usual thing, and on this side we have the vortex theory. Let me call this phi. And again, if I had an external electromagnetic field, keeping track of travels to the current, the U1, current conserved U1. Over here I will have this external electromagnetic field coupling to the curl of the voltage. And again, you have the Maxwell type. Okay, so it's very similar to this, except one difference is that 2-pi vortex of this boson corresponds to this psi over here, and conversely, the flux density little a divided by 2-pi is the charge, the original U1 charge. Okay, so again, you have similar kind of things. If you want to identify what is the operator that corresponds to the boson, it's actually the monopole insertion operator. And again, time reversal and particle load are interchanged. Okay, but so now let's see what this gives you. So one of the things that gives you is that you can study a phase diagram.
Sorry, once again, this is conjectured to be a complete duality in the IR. But the IR description of that is exactly the.
Okay, that's a good question. So there are two levels at which you can make this duality. Right. So there's a strong and a weak. Okay. So this is the strongest statement you could make is that take this. So the interesting case is when this thing is gapless. So then you have some kind of a QED. But if you want to really define that QED, you have to put it on some lattice and say that the coupling constant is very small. And then let it flow, and it gives you some non-trivial fixed point. Okay, and the strong form of that duality is to say that that fixed point is the same as the Wilson-Fisher fixed point. Okay. And apparently this is true, but you have to do numerics to show that. Right? You have to actually start with. I don't think you can just sit back and think and say that's true.
But there is some other lattice regularization on the right, which is exactly.
Yeah, but okay. So there's a weak form of the duality, which is.
Sorry, just from what you said, so it's an equivalence between two conformal field theories that you flow to in. So it's the Wilson-Fisher fixed point, and it's dual representation.
Yeah, so the weak form of the duality is, I can tune various things over here, like, there's some S-squared, 7/4, etc. I can start with some lattice model and tune various couplings, and then I let it flow, and at some value of the coupling, it gives me the Wilson-Fisher fixed point. Okay, that we know to be definitely true. That's the weak form of the duality. That you can, start with this theory and or if you like, start with this theory and you can do some exact transformation to this with some very complicated interactions, but local interactions. Okay, so to say that's the weak form, right? But the strong form, which is which needs numerics, is to say that some well-defined limit of this, which is QED3, and QED3 is only defined if you can explicitly identify a field which is this is a boson field, this is a gauge theory, it's weakly coupled, you can separate it out, and then it flows to the Wilson-Fisher fixed point.
Another question: the supersymmetric version of this is that exactly velocimetry on the boson side?
No, I think it's the free boson. Here's the Wilson-Fisher version.
Yeah.
Okay, apart from the Wilson, I see. But it's possible that integrating out the fermion generates a Wilson-Fisher.
No, because it's decoupled. It's a free boson.
I see.
So one question: why are you focusing on the Wilson-Fisher fixed point? Usually we think that even phases are described.
Yes, yeah. So phases definitely you can describe with one.
And some stable fixed points are also represented in both.
Yes, yeah. That's the okay. So let's say I had some coupling over here. G is fine, I guess. Okay, so you have two phases over here. G is very large. Okay, then this is some disordered phase. And there's an ordered phase when G is small. And you can ask, how do I describe this in terms of vortices? Okay, and so there's some other coupling, let's say G prime or something like that. And it turns out that in the it's of course the strong weak kind of duality. The disordered phase over here is like Higgs, the condensed phase. Where the psi in some sense has got an expectation value. And on the other phase is when the psi is gapped. Average psi is 0, again within quotes because it's not a gauge invariant operator. And this is like the gapped insulate, we should call it the Coulomb phase. Okay, so certainly any phase of this model you can identify, by just taking various limits of parameters over here. Okay, and the gapless excitation, the Coulomb, the photon of the Coulomb phase simply corresponds to the Goldstone mode of the ordered phase.
And so the weak versus strong subtlety is what now? Yeah.
So in the phases, I don't think there is any
there's no
there's no distinction because we kind of know what to do over here.
Right.
The non-trivial question is about this.
About the physical
Yeah.
So then the phase transition is what you were calling the Wilson-Fisher fixed point is the phase transition.
Yeah.
Is that right?
Yeah. And numerically, what people do is I don't know how well they're able to take this coupling constant to 0, but they take some coupling constant and they look at the low energy physics and they find the same exponents as Wilson-Fisher. So even if it is not very well defined QED3, they can easily find there's a large range of parameters where they find Wilson-Fisher fixed point, but using these other variables. So I don't know where that falls in this strong versus weak. It's somewhere, even if it is not exactly the strong form where there's a very well-defined theory, you can find it. You can find the Lagrangian that corresponds to this fixed point. Look, I'm happy, sure.
No, I'm happy.
Okay, so let's try to do the same. So like we did over here, we could identify the different phases of this on both sides. Let's try to do the same. Let's try the same strategy over here. Okay, so let's. I'm told this part will not be shown on the. Maybe I should just erase this.
Well,
nobody there.
Those guys?
Show them, Ashvin.
All the cool stuff will be over here.
okay, we can turn that off.
You see them tearing their hair out.
For the recording.
No, for the recording here. Oh, sorry.
Okay, so let's have some sanity checks over here. So the first one that I will do is, let me introduce a finite background magnetic field on the left-hand side. Okay. So again, we're going to talk about, we'll discuss later whether this is the strong or the weak form. The weak form is definitely true that in any phase that I have over here, I can find some representation of that phase using these different variables. Okay, and so let's see how we can represent that. When we deform this with a finite background magnetic field. Okay, so what happens when you have a magnetic field? Well, you have these are Dirac particles. You apply a magnetic field and you get lambda levels. Okay, but the lambda levels of this problem are kind of special. They have this particle symmetry. This is n equal to 0, n equal to -1, n equal to +1, etc. Okay, and all the if you have this kind of particle symmetry, then this has to be exactly the chemical potential for the Dirac node is you started with the Dirac theory, and the chemical potential is right at this neutral point. Yes, only these states are filled. So when you look at the lambda levels, all the negative lambda levels are filled, and the zeroth lambda level, which is exactly at zero energy, is half filled. Is this familiar to everyone? Everyone in condensed matter knows this because of the field. It's exactly half filled. Okay, so basically what you have is a half filled number. Okay, we call it mu to the half. And if the interactions are right, what happens when you have this plus some interactions. So that's the dot over here. If you didn't have interactions, there's something singular about this. But once you have some interactions, it's actually known that certain kinds of interactions end up giving you a composite Fermi liquid. Okay, so it gives you a metallic state. So we can ask from our duality what this would do. Okay, so we have a finite density of this curl of A.
Ashvin?
Yeah.
So when you say it's known, that's kind of the inverted code, right? I mean, it's known in some quadratic sense, correct?
No, it's from numerics, let's say. Take
Oh, you're talking about the numerics.
Okay. So maybe I should invert the order. Let me take this mapping and see what I get. And then I'll tell you that that's actually what's realized numerically by people and experimentally as well. Okay, so we have a finite external electromagnetic field. So let me do integration by parts. I'll get curl of A. That's some finite number times little a. Okay. So that is basically a chemical potential for these composite fermions. Okay, and it gives you a finite density. We can read it off from this. The flux density that you get. So this is number density is equal to flux over here. There's an equivalent relation that if you have an external magnetic field, okay, so B divided by 4 pi, this other thing will be the density of composite fermions will be related to this external.
In terms of symmetry, so when you put on the magnetic field, then the time that this symmetry is B going to minus B is also required for this symmetry?
Not for this implementation.
Not for, but if you do the...
Yeah, so that's why I've chosen a kind of way to...
So this remains...
this remains a symmetry. You lose the time reversal symmetry of the usual time, psi goes to psi.
Right.
But this anti-unitary psi goes to psi diagonal is still the same.
Without changing the field. With the same.
Yeah.
Without
If you like, this is kind of... this is like how a magnetic charge would behave.
That's how.
Well, so if I have time reversal symmetry, so if I think of the psi as being electric charge,
Yes.
this operator takes electric charge to minus electric charge, but that means that it keeps the magnetic charge the same. So the magnetic field is not changed. I don't know if you have a question or you're just restless.
I'm not sure I got the punchline. So punchline was that if you turn on magnetic field on that side, it's like turning on a chemical potential.
Exactly, yeah. And the chemical potential is such that it gives you exactly a certain number of these gate charge particles. It gives you n composite fermion equal to 1 over 4 pi times T external. So if I draw that over here, initially, before I put on the magnetic field in the dual description, I just had QE3 with chemical potential sitting at 0. Now, in the presence of this external magnetic field, it rises up to that point. Okay. And of course, there's no magnetic field acting on these things, which corresponds to being exactly half filling for the original electrons. Okay, so what this picture is telling you is, if you put on a magnetic field on the right particles have a half fill lambda level, you should be able to describe that physics in terms of some liquid of fermions coupled to a gauge field, which is this dual description.
So there's a non-zero density of the composite fermions on the other side. What was worrying me was that I thought that this would have this would be an infinite energy.
Okay, but this is like there's a background charge density.
Okay.
Right. So if I have a gauge theory and I put in a background charge density,
then it gets green.
Yeah, this is normal. This is the normal thing. And the background charge density is played by the flux density.
I see. Thank you.
So you presumably when you crank up the field to do this, you pay a lot of energy.
I see. But actually, it's actually more accurately a background charge density than a chemical potential, right?
Yes. Yeah.
Okay.
because chemical potential doesn't actually make sense if you have some gauge charge particles.
Yeah, it's just a term, a Lagrange multiplier term.
That's right.
A times B.
Yeah.
Yes.
Okay, so this, so people can numerically check if I have half-filled nano level with various kinds of interactions, you in fact get this sort of metallic state, and this is called the composite fermion liquid, and it's been seen in experiments in numerics and so on.
Say that again. What can we check?
That you just take a Hamiltonian with a half-filled nano level. Actually, you don't even need a Dirac thing because if the interactions are weak enough, this is the only the only important dynamics is all occurring within this first nano level. So it doesn't really matter whether you start with the Dirac dispersion and put on a field. You could take any old dispersion, put on a field, have a half-filled nano level with certain interactions. And what you find is that even with the regular interactions you have between electrons, you find that the state you get is not a fractional quantum state, but it behaves like this metallic state. It looks like it has a Fermi surface with a certain 2kF that's set by the flux density.
Ashvin, that statement is not completely correct because there's an empty question. I can certainly create situation where d is equal to half. You have a Pfaffian state.
Yes.
So that's not described by this theory. That's the point.
No, it is described.
It is?
Yes.
Oh, then I'm good. Then I really will wake up now.
Yeah. I mean, as you know, the Pfaffian state is some sort of paired state of composite fermions.
Yeah, but that will come out of this.
Yeah, so if I have this Fermi liquid, you could also imagine that there are
Form a pure superconductor from there.
the particles and can get some kind of superconductor.
With
What kind of superconductor we talk about? Because that's the really interesting thing. It tells you the Pfaffian is not the most natural state to get. There's a different state which is more natural.
But you needed interactions to get the composite fermion from liquid in the first
Yes.
place. So what characterizes this? Like which way is it?
That is the kind of question we cannot answer. I mean, if I could answer that, I wouldn't tell you the answer.
So that's part of the dot.
That's why we talked about the universe.
But we have certain sensibilities. We have certain. If you tell me what you got over here, I can find a way to get it over here. That's the same as over here. Here, okay, you can say there's some G or something like that, some coupling constant. But in reality, you may not know the exact mapping, but you know how to find that phase.
Just to, I'm sure you will say much more about this, but where did you need the Dirac particle so far, at least for
Yes.
this?
Yeah. So you didn't need it yet.
Okay.
But I'm going to. But now, one thing we can discuss over here is how does symmetry act? Okay, and you couldn't do this if it wasn't a Dirac particle. So a Dirac particle has particle symmetry, and you continue to have particle symmetry over here. So
even though you are up to without the
no, I'm talking about this description. And what that corresponds to over here is time reversal symmetry. So in terms of composite fermions, the particle symmetry of the Dirac particles is time reversal symmetry over here. And sure, this has time reversal symmetry. Okay. But the way in which time reversal symmetry is implemented is very interesting over here. These composite fermions are actually Kramer's doublets. Okay, so and the Dirac structure is coming because they have like a spin up and spin down, which is coming from this Kramer's degeneracy. That's this degeneracy over here, and that is resolved by this momentum. Okay, so if you plot the spin, on this Fermi surface, it has some sort of texture.
even though it will delay you, those of us who don't have good education, can you just explain the Kramer doublet?
Okay.
Sorry, I know it will slow down things.
Okay,
Just
yeah.
2 minutes. If you don't mind.
Yeah. So. Okay. So.
Some language that is not entirely.
Yeah. No, actually, it's not taught in quantum mechanics, and I didn't know it. And topological insulators were discovered, and then you have to learn it. Okay. So let's say I have electrons spin up and down, and so these are two states which have the same energy. And usually you think because you have spin rotation symmetry, they have the same energy. So there's a generator that commutes with the Hamiltonian that relates these two states, so they have the same energy. Okay, but what this Kramer showed was that you don't need to have any spin rotation symmetry. All you need is time reversal symmetry. Okay, so if I have time reversal symmetry, which is an anti-unitary operation. So if I have time reversal symmetry, anti and spin out, it goes to spin down. And time reversal symmetry acting on spin down goes to minus of spin. Let's say this is how these things transform on a time reversal. And so then if you look at what is T squared acting on any state, it's that. So now you might think that this, I can always change the phase of the wave function. Right? So is this real or not? So let's try to do that. Let me take a new state, prime, which is, okay, so now if I act time reversal on this up prime, okay, so that's, and this is an anti-unitary symmetry, so this will go to e to the minus 9 prime, and this is a full prime. Okay, and then you act again. Actually, I won't do the algebra, but you can do that and show that despite having this phase factor, you'll get two of them that cancel out, and you'll again get this minus sign. So this minus sign cannot be gauged away. It's related to this symmetry, and if you regardless of whether you have spin rotation or not, because you have this Hamiltonian commutes with time reversal, these two states have to be degenerate. Okay, so
basically, anytime you have a time reversal symmetry, you're going to get a doublet, and that's
yes, yeah. The thing that's very different from we are used to symmetry giving you degeneracy, but in all the other cases where you have a unitary symmetry, you can label the states with some quantum numbers. You can say that they have two different quantum numbers that you can relate by some symmetry, and therefore they are degenerate. The thing is, because this is an anti-unitary symmetry, there are no quantum numbers. You can't really call them up and down. There are just two states. There's no label that you can, there's no invariant label you can attach with the eigenvalue of some operator, but yet they're degenerate.
But Ashvin, isn't it almost equivalent to the field theory fermion doubling theorem?
So fermion doubling has to do with having a lattice.
Yeah, I mean, this is a continuum version of that, isn't it?
No, this is like a zero-dimensional statement.
Okay.
You have one side and
this is true for you.
Okay, so the composite fermions have this Kramer's degeneracy, and they have it because of particle-hole symmetry, the original particle-hole symmetry. Okay, so this theory actually, this way of thinking about the composite fermion liquid, makes a physical statement. It says that this composite fermion liquid, which people knew about before, it actually says that it's a Dirac one. If you have particle-hole symmetry. So actually particle-hole symmetry is not exact in real systems, but it's very close to being a symmetry. You can more or less forget about all of these lambda levels and just look at this. So this is something that people can go and test. Is this a Dirac particle? The thing they knew about all along. There's a subtle distinction between, so the limit that they generally think about is there's a mass term over here to this thing which breaks the time reversal symmetry, that's like breaking particle hole. And then the mass is large compared to this chemical potential. It's like you're in the non-relativistic limit of this Dirac particle. And then there is no kind of spin texture around this. That's the usual theory. But now we say that there's a spin texture that gives you a very space of pi when you go around. That's the thing that's special about Dirac particles. And that's something they can look for. It's a very subtle thing to look for, but you can come up with experimental probes of this.
So the significant thing is that t squares is acting with a minus 1 on some scale.
That's one of the significant things.
That's the pi. That's what I
No. That minus 1 is important. That's one thing. The composite fermion is actually a Kramer's doublet. Okay, that's one.
So are those two statements equivalent if I have a state where t square acts on it and gives a minus sign to that state?
Is that
and I'm
equivalent?
guaranteed that
That's a doublet.
It's not guaranteed to be Dirac-like.
No, I know, but it's
Yes.
guaranteed to be part of a doublet then? Is that what?
Yeah,
you are
if t
saying?
squared is minus 1, then there's always a doublet. Yeah. There's a degeneracy because it is Kramer's-like. So electrons are also Kramer's-like.
Right.
But the thing that's very different over here is these have only a single Fermi surface.
Yeah,
If I give
usually,
you
yeah, we have two.
Yes, you usually have to.
Spin up and spin down or something.
Exactly,
Less
yeah.
spin,
So this is very weird to have this one. In fact, it violates this fermion doubling theory. But in a sense, okay, the original theory also violates fermion doubling. That is, you have a single Dirac group.
And bosonic states never have t squares varying to minus 1. There is no such naive.
You can have, but they will always carry some gate charge. Bosons that we see
Are always.
are always that t squared equal to +1. And the reason is if you have t squared, if I just give you some, bunch of these particles. So t squared equal to plus 1 is normal, right? T squared minus 1 is weird. So, for example, with fermions, you always can create fermions in pairs. So you're never in a situation where you have your overall system as t squared minus 1. You can look at part of it and say t squared is minus 1. But they always create in pairs. But if you have bosons, you can imagine creating one of them. Unless they carry gauge charge, then you can't create one of them. So the only things that carry t squared minus 1 are non-local operators, like fermions. You can't add it to your Hamiltonian.
Yes.
So sorry, but just to understand. So you're saying, suppose I had enough of the charge density and I filled up to some point. Then you can still just staying on the Fermi surface and going around, tell that there was a Dirac dispersion, not a quadratic one, even though that's so far away.
That's right, yeah. In fact, that's the only real effect. The things down there are not really particles. The only thing that is real is the things near the Fermi surface.
Right. But you can still do this go around.
Yes, yeah. So that is the only content that there's a base case of pi going around. This is a very subtle thing that you can try to,
Is the physics of these composite fermions sort of like a free Fermi liquid?
No.
Because of the gauge exchange, it's strongly coupled.
Yeah. So it's a non-Fermi liquid.
It's a non-Fermi.
Yeah. Okay. It's somewhat, if you have long-range interactions on this side, it's somewhat, and in fact you have one over R interactions between electrons, Coulomb interactions. So it turns out it's just a marginal non-Fermi liquid. There's some weak corrections to the
Is pi very fixed that affects the Pfaffian-like wave function you get when you condense these things?
Yes, yeah. So now we can talk about other states that you could get. So you could get this composite fermion liquid, and then you could imagine pairing the fermions to get a superfluid. And the simplest way to pair the fermions is you take one at k, and you pair it with minus k, and you just go all around the Fermi surface, do that uniformly. So that's called a Foucault superconductor.
What?
It's called a Foucault superconductor. So this is like the surface of a topological insulator, and you can put a superconductor on top. So what you get when you condense pairs of these particles? Well, these are some gauge-charged objects. You take pairs of them and condense. That's some Higgs space. So the gauge field is gapped. Everything is gapped, in fact. So this is some theory that's completely gapped, but it has some non-trivial topology. It has topological order, and you can try to quantify what the topological order is. And you can just figure out by looking at the vortices of this theory what the topological order is. And it turns out that this topological order is actually a non-abelian topological order.
You just look at the zero modes of vortices and see there are Majorana's and just get some icing like that.
Yeah. So there's an icing part, but there's also a charge mode. This little a, this big A. So there's an icing times some abelian part, which takes care of one effect. Because this is like a half-real lambda level, you should have sigma xy to the half. And there's something like some abelian part that keeps track of that. So this is very close to the what people call the Pfaffian thing, but the Pfaffian is actually icing times U1. So it's like you have at the edge you have a conformal field theory. There's a right mover that carries the charge, and there's an upstream in the simple superconductor.
Upstream means left mover.
Moving against the charge mode. Whereas the Pfaffian has both of them moving in the same direction. So they are different topological orders. So the Pfaffian actually corresponds to some more complicated way of pairing this composite fermions in this one. It's like a D plus ID pairing of these composite fermions. And there's a time reversed of that. That's called the anti-Pfaffian. That corresponds to a particle hole on the original problem. So the things that people believe are experimentally observed are this Pfaffian and anti-Pfaffian. One or the other.
They're different states.
Yeah, because you don't have, they are related, but they spontaneously break time reversal. And there are two ways of breaking time reversal.
What's the Chern-Simons description of the mesh U2 or level 2?
Yeah, roughly speaking, but it's more complicated than that because they are not built of bosons, they're built of electrons. It's a non-modular theory, if you like. So there's a lot of discussion about the field theory, but SU2 level 2 captures a lot of it. Times some other U1 factor. but then you divide out by one particle, which has no statistics with anything else. There's an electron in the problem which has no mutual statistics with anything else. So that's called non-modular theory. You take this product, you can take SU2 level 2 times U1 level 8, and then you find a particle that you condense and get rid of all other particles that have mutual statistics with this particle, so that you get an operator that corresponds to the electron.
It all sounds non-topological.
So there's stuff that still remains after you do this procedure. So it's still topological. But anyway, we'll talk about that later.
Really sorry, just to make sure I understand. So this is a sanity check for the following reason, that it's well known, if you just take the left-hand side picture, you add some amount of flux, it corresponds to half filling, and it should give you this.
Yes.
And then you reproduce it.
Yeah, you reproduce, yeah. And people can show that you get this numerically from numerical experiments.
It's on the left-hand side.
The left-hand side is just free fermions, right?
But you have some interactions to get something interesting. But it could still be true that at very low energies these interactions are irrelevant. You put in a magnetic field, so you get a length scale, and you stop all the RG at that length scale. So you have some residual interactions between the particles to get some sensible answer, and that can be reproduced on the right-hand side. Yeah, so certainly this, that's one check. It doesn't prove this, of course, but it's consistent with this. The other thing you can do is you can imagine adding a mass term over here. Okay, so that's the second sanity check. So now you break particle or Tangle-Russell symmetry. So just add a mass term. Okay, and so everything is gapped on the left-hand side, and you can integrate out the fermions and get an effective theory for the external. This is just a response theory. There's really no at low energy. So what you get is, it's a single Dirac cone that is gapped out. So it's 1/8 pi A. And that just corresponds to having an all response of 1/2.
John Simon's at level half.
Yeah. But this is an external gauge field, so that's okay. But now, what about on this right-hand side? Okay. So again, you break Tangle-Russell symmetry on the right-hand side. So the most natural thing to do is to again add a mass term over here. Okay, and so let's integrate out the fermions and figure out what we get. So this is right-hand side. Okay, so now you get, again, this 1/8 pi A. Okay, so now you should be a little bit alarmed that you got half. We'll talk about that, why this is, why that's not a problem. And now you have this response. Okay, so anyway, this is some Chern-Simons theory for the little a. So again, everything is gapped. That's consistent with this left-hand side. And you can integrate out the little a, and what you find is, if you have the right signs for the mass term, you end up getting the same. All conductance. So again, that also reproduces this.
So on the right-hand side, the symmetry you want to break is this time reversal?
Yes, which admits a mass term.
Which admits a mass term. And on the left-hand side, you're breaking this anti-unitary particle.
Yeah, which also allows you to mass term. So that's the most normal thing, and in fact, they check out.
You're not saying it's actually that side by side maps to side by side. You're just saying it's at the right symmetry. So anything you do it, you do the same.
Yeah, so if I put in a side by side over here, it has an overlap with the operator side by side over here. Why not?
It's uncharged and converges.
Yeah, and it breaks the same global spaces. Okay, so that is the other sampling check. But what you notice is that for this to be true, so this is the parity anomaly. The fact that you're allowing for a half integer Chern-Simons term, this is k to the half, for a dynamical gauge field, that is usually trouble. Right? And if you go back and see why that is trouble, you can take this Chern-Simons theory on a compact manifold like torus, and then you can rewrite it as a quantum mechanics problem for the two fluxes around the torus. And what you find is that if the level is not an integer, shifting those fluxes by 2 pi, which should be nothing, actually give you some change in production potential. Okay, so that there is a problem, and the way you can resolve that problem is by modifying the compactness conditions in the layer.
Which is your vortex is charged to.
That's right, yeah. So we'll see that comes out very naturally from this electric engineering duality.
Being resolved is by changing the compactness
Yeah,
condition.
so A goes to A plus 4 pi
I see.
is the compactness condition.
Which you can absorb it changing the charge of the composite fermion. You can rescale your A so that you get a 2 in the magnetic. Or half.
And not really. So you want to, okay, so you want to say the fundamental monopole is this guy. And
If you allow monopoles of charge 1, then you'll have electric charge 2.
yes, but then you're minimally coupling to charge half. Right.
No, that becomes charge 2.
Right?
It becomes 2 there if
You want to have charge 2 over here.
and then you allow monopoles of charge 1. I think it's just a redefinition of your A.
No, there's some physics over here which is that, there is something which is normally the single monopole, and you're not going to allow it. Right? And you can't kind of, just rescale things and get rid of that.
And you can rescale it so that I allow single monopoles at the expense of having a charge 2. I think this
But then there's a half monopole which is natural from the Dirac condensation condition
That you don't have. Yes.
that you don't have. So
Right.
it maybe notationally it looks better, but it's actually the same problem. There's a natural monopole that you kicked out. Okay, so
I see. So you don't like that notation just because there's a half monopole in the game,
yeah.
which you're going to forbid anyway. But
Yeah, I mean, you are prejudiced against the half monopole because this one like is half, but actually it's charged 2, so half monopole is valid. Should be a valid extension.
So then the actual sort of the statement on the right hand side is it's this theory plus this condition that forbids
Yes,
some.
yeah. Or if you like, the single monopole insertion operator is not a local operator. It's some weird thing that shouldn't be admitted in the theory.
So the Hilbert space is that of this theory plus this constraint. That will
Plus,
allow
yeah,
some-
only even strength monopoles. And the way it will come out from this duality is that the single monopole, we'll see that the bulk is some condensate of double monopoles. So you're allowed to, and the surface theory is what is going to be in this theory. So when you admit double monopoles to tunnel, it's fine because they go into the condensate. But if you take a single monopole into the bulk, then it's changing the bulk. So you can't just talk about the surface theory. So
just to understand, so far you hadn't actually fixed the periodicity of little a,
yes.
and now you're saying, look, this adding the mass term fixes it to the.
Yeah, this is a concept. I mean, the mass term makes it explicit because it's some. Also, people don't like this. Why has no one studied this QED thing with one flavor? They say, oh, it has pattern on it. And they add a Chern-Simons term to cancel that off. So all the theory, generally people don't study this kind of theory. They have a half, little later, D, little later.
I see. You're saying equivalently you can just posit that A has this period.
Yes.
And then you can.
Yeah, and then you can make sense of it. And it's not random. What I'm trying to say is that if you do this three-dimensional duality, you also get the same condition for some very physical reason.
just a comment. The one place this theory appears naturally is an SU2 gauge theory with an adjoint fermion, and then you kick that down to a U1. In fact, if you were here 4 hours ago on this same blackboard, Hugh was talking about monopoles of charge 2 and electric charges of charge 1, precisely in that.
So how come you don't have the unit charge?
Because the unit charge would correspond to fundamental matter charge of the SU2, and you just have a theory without fundamental matter, just adjoint matter. So it immediately gives you kind of coupling. There's no hint of a hidden SU2 symmetry in the game.
Well, I want to understand that. Why the Dirac condensation condition is not working? You're getting monopoles that are multiples of the basic monopole.
So maybe there's some issue of culture here. So if we took an SU2 Yang-Mills coupled to an adjoint scalar, then there's a smooth soliton configuration with the top of polio coupled monopole, which is the only smooth soliton. It has double the allowed magnetic charge.
So eventually you get a U1 gauge theory, right?
So that's SU2 broken to U1. And the smooth topological monotone has twice the charge allowed by Dirac quantization. And the reason is that if you were to add a fundamental scalar to the game, that would have half the charge of the adjoint matter. And therefore, it would have the right Dirac quantization relative to that. But if you just have SU2 with adjoint matter, naturally gives you the kind of factor of 2.
But why can't I just have some fundamental matter?
You can, of course, but you get a choice to.
Okay, so then you're going to forbid the fundamental matter. You're going to, by fiat, say that there's no fundamental matter in the world. That sounds a bit like this constraint, right? You forbid it having.
I guess maybe I should help with it because I just don't write down certain fields in the Lagrangian rather than forbidding something that's not hidden.
It may be like a cultural thing, right? If it's not forbidden for me, you've got to write it. But you're saying it could be that you have something that is somewhere. Okay, so am I out of time?
No, you just go.
Okay.
You can go to 6.
Oh, really?
At least.
So I think what we are, so what I'll also argue now is this weak form of the duality. But the interesting conjecture is that maybe a strong form of the duality works. Okay, in other words, that if I give you QED3 like this, I start with a lattice model. I have these fermions hopping around lattice, weak coupling to an electromagnetic field. I let it flow to low energies. Well, first of all, it has to be stable. It shouldn't generate a mass gap. Right? But let's say it's stable and it goes to some fixed point. The strong form of the duality conjectures that's simply described by the free Dirac form. And that would be the simplest way in which this duality could be.
Now you really mean free, not these dots that you need.
Yeah, asymptotically it's just free. Because if I add some short range interactions over here, they will flow to zero if the short range interactions are there. Yeah. Now the trivial statement is that if this thing has some fixed point, again, start with weak coupling flow, and it goes to a non-trivial conformal field theory. You can certainly represent that in terms of the left-hand theory with some dots.
Right.
But that's just saying that this forms a complete description. But if this is very strong, what does that even mean? Right? It's just some. Yeah. How do you treat something like that?
And the weak interactions that are formally irrelevant in the R3 will be enough to get you a equals half. It. I mean, if I just thought of the left.
Well, if not, that depends on what length scale you stop at. Right? If you have some magnetic field on with length scale,
right,
that gives you some energy scale because it's not quite flown to zero.
Right.
And that will set the energy scale of the dispersion of those composite formulas. So it's not relativistic. So
that's
this dispersion is set by
energetics.
Right. And if that is very weak, then the dispersion, I guess, gets flat.
Yes, flat.
Okay.
I'm saying. The statement for this duality is not similar, as in there are two phases and the CFT sits in between. So
well, yeah, because you have a symmetry, you don't need that. The symmetry prohibits the mass term.
So you're in the middle of the phase.
Yeah, so you're already at the. You could conceive of
you might just want to break it and then have a similar.
Yes, you're right. Yeah. So you could want to, if you like, you can tune the time reversal breaking, and then you will be between plus half and minus half.
Oh, I
and
see.
this will be the critical point between that.
Okay.
And there are two candidates. So the question is, suppose I have this kind of, it's like an integer formula transition. So just like this, yeah, you have. Okay, and there are two ways of doing this. You can do it on the left-hand side, you can do it with the mass term on the right-hand side. And certainly these cases are the same. The question is, is the critical point the same? It could be that there is some other axis over here. This is the free theory. This is some interactions on this, like the dots. And I have to tune that, and if that's very small, then this is a fixed point. And if it's very large, then there's another fixed point over here, which is naturally accessed by the screen. That could be the structure. That's the other non-trivial option. And there's a third option, which is the most boring one, which is this is a first order transition. Okay, in other words, this is actually unstable. You start with QT3, weak coupling, you flow down, and it just generates a mass gap, spontaneously breaks the standard Wilson symmetry. That's like the first order transition.
Right.
And somehow you might naively think that is what will happen, because usually you think small number of flavors, QED is unstable in 3 dimensions. But there's actually a caveat. When people say that, it's because they always consider like 4-component fermions. And the mass term they're thinking about is something like a plus mass for one of the 2-component guys and a minus mass for the other 2-component guy. So if you do it in something like large N, those kind of mass terms are the most relevant ones. But this quantum Hall mass term is actually less relevant. So that intuition may not be right for these 2-component odd number 2-components.
This mass term just also breaks the symmetry.
It breaks the symmetry, yeah. Unlike the other one. The other one breaks some flavor symmetry but doesn't break time versus zero. And doesn't give you a Hall conductance. Yeah, so those are the 3 options that. Okay, so the last part is anyway. So if any of you have some ideas how to prove or dispose of this strong form of the duality, that would be interesting. And it has to be something like some supersymmetric definitions or something like that. And I think there are, what I've heard from people like David is there are supersymmetric theories that smell a bit like this. There's some complicated, QED like supersymmetric theory on the right hand side, and there's a dual to free fermions on the right hand side. But it's never like one copy. It's several copies and all kinds of stuff along the way.
I learned of a new one, which you might want to know. SU2 coupled to adjoint matter, but with Chern-Simons equals 1, is the same as a free matter.
Free Dirac fermion.
It's all supersymmetric, so it's a free Dirac fermion plus a free scale. Everything I said above is
I see. A single Dirac fermion. A single 2-component.
single 2-component.
Oh, okay.
The SE2 has a Chern-Simons.
It has a Chern-Simons, but there's also extra fermions, which if you were to give them mass and integrate them out, will kill that Chern-Simons.
Is that?
The glue we use.
Are you sure that's right?
Yeah, I think they shifted by exactly 1 because they're in the edge.
Is there a name for this? Who's the?
It's by Xi. It's called duality appetite. By Yin and
It's a particular example of Gibeon Buddhism.
Who's duality?
Gibeon and Buddhism. It's just the associatism there, right?
But it seems interesting because, as I said before, it's SU2 with stuff only in the adjoint. So if you break to a U1 somehow, it naturally gives you the right monopole charge.
I see.
Adjoint.
Okay, interesting.
I can send you.
And she is around, so someone.
She's around.
All right, so let me finally talk a little bit about the selective magnetic duality, where this, if you want to try to prove this, where it comes from. Okay, so let me remind you very briefly what. So there's now we're going to go to 2+1D, and we're going to have a U1 gauge theory. Okay, let me first do the bosonic version. Okay, so the charged particles are bosons, and they have some charge. But you also have monopoles in this theory. Magnetic monopoles. Okay, and they have some magnetic charge, integer magnetic charge. And if you have a theory like this, you can write it in 2 different ways. You can write it as like that, just the usual Lagrangian in terms of the electromagnetic vector potential. But there's also a dual way of writing it in terms of the magnetic charge. And this is in terms of some new vector potentials, such that the electric and magnetic charges get exchanged. Okay, so so you have a lattice over here of electric and magnetic charges. They take on integer values. Okay, and instead of calling this the fundamental particle of your theory, the electric charge, okay, what you can do is you can sort of invert this picture, talk about this as the charge of your theory, the magnetic monopole, and then this electric charge will be the monopole of that theory. Okay, so it's just a shift in the way in which you think about it. But what it does effectively is it changes your coupling constant from E to 1 over E, okay, where 1 is 2 pi. So there's some strong to decoupling kind of duality here as well, which involves an exchange of the electric and magnetic particles. Okay, so that's of course sort of trivial. What we're going to do is we're going to do two things to generalize this. We're going to talk about fermions. And usually people don't make this distinction, but it's a very important distinction whether the particle that carries the electric charge is a boson or a fermion. And we're going to talk about fermions. And the second thing we're going to do is we're going to pay attention to symmetry. Okay, in particular, we're going to pay attention to time reversal symmetry. Okay, and we'll see that there's a particular theory. Okay, so I'm going to go to fermions. And I'm also going to do one more thing. We're going to have a non-trivial theta term. And I'm going to have time reversal symmetry. I'm going to pay attention to time reversal symmetry. Yeah, and the only options for the theta term when you have time reversal is 0 of pi, and the non-trivial one is pi. So we'll talk about that. So we'll write down a theory. We'll start with a theory that is built of fermions as theta equal to pi with time reversal.
So you're going to pick one of the charges to be found.
One of the charges to be?
Fermions. Electric, one of them.
Yeah, let's say electric.
Okay.
Yeah, I'm going to start with electrons. Coupled to electromagnetic field, it's a fermion. I'm going to put those electrons in a band structure of a topological insulator. That's going to give me theta equal to pi. It's going to have time reversal symmetry. And what I'll do is I'll show there's a different way, a completely different way of describing exactly the same theory, where I'll give primacy to the monopoles of the theory. I'll call them my particles coupled to some gauge field. And we'll see that there's a dual thing, okay, where again there are fermions. Okay, but here the time reversal will act as particle. Okay, and by having these two descriptions, by relating these two, we'll be able to derive the weak form of this duality. Yeah, and this was actually done by Max. I'll tell you what's exactly. So we won't actually prove this in gory detail. What he did was to calculate the partition function of this theory, calculate the one for this one, and equate it, and show the equal. And you can do that on any math board. And you need to do that on any math board.
So this is now in 3+1D.
3+1D, yeah.
And we have fermions with the U1 gauge.
Okay, I'll describe. I'll let me because it doesn't make sense with what I just said. The details are interesting. Okay, so the first theory that I have is I have some fermions that we call them some psi. I have some time reversal symmetry. So psi goes to psi and I goes to minus psi. There's some matrix epsilon. Okay, and I have some Lagrangian, which is psi bar. There is some mass term, psi bar psi. Which is time reversal invariant because we are now in 3+1 dimensions. And there are two kinds of mass terms you can write down with and without this gamma. And these gammas are on 4x4 matrices, usual Dirac matrices. Okay, so this is the theory, and I have, of course, the usual F squared term. Okay, so let me now think of integrating out these fermions, and I'll do that in the large mass limit. Okay, and what they do for you is they generate a theta field. Okay, and so they will give you okay, but the only values of theta that are time reversal symmetric are theta equals 0 and pi. Okay, so, and we focus on this theta equal pi. Okay, so this is one theory. But the theory that this will be dual too. Okay, so let me call it composite fermion. It looks very similar. Okay, etc. etc. So I'm specializing to the case theta is equal to theta is equal to pi. So I zoom down 5. Okay, but so this is some fiddle, and we'll see that this is the dual, which I think is true. Okay, so it looks like this original theory, but the difference is going to be that under this time reverse, the same symmetry, this composite fermion goes to its stack. Okay, so this is going to be actually transforming like a magnetic part on the time reverse. So this is an equivalent description of this theory, not in terms of the electric charges, but in terms of the magnetic charges. And the magnetic charges will also be fermions. And they also have this theta angle of pi. And the way you can see their magnetic charges, among other things, is this is how they transform in time reverse. Charge goes to minus itself. Okay, so the poor man's way of proving this is to look at all of the particles in this theory.
So this is a 3+1D duality in a sense.
Yes.
Right?
Yeah.
It basically exchanges the electric charges with the magnetic.
Yes. But you'll see that the electric charges are actually exchanged with the double monocle. And once you establish this, you can derive this duality. Because it turns out that the surface states of these two theories are actually these two, will be related to these two things. Okay, so the poor man's way of doing it is to look at all the all the particles here, the electric charges, the magnetic charges, and the ions, and show that they have the same qualitative properties as all of the things over there. For example, the statistics, how they transform under symmetry, and so on. So that's not quite a proof. The real proof you want to do is to actually show the partition functions are the same. And that's above my pay grade, but Max can do that.
So, what is the nature of that four-dimensional duality? Is it supposed to be exact or sort of IR duality?
This is an exact duality in the large mass limit.
So in the large mass limit, in the large mass limit, the only thing you have is free U1.
If you fix the geometry of the system, yeah, that's right.
So both sides you just have free U1.
Yeah.
So then what's the content of that? I haven't understood.
Okay, so you're saying it looks like this is trivial, right?
Right.
They're both U1 gauge theories with theta equal pi.
Right.
But that is if you, let's say you define your system on some topologically trivial space. But in general, this also holds on an arbitrary space, including non-orientable manifold.
Okay.
And then you get like this, you have to also sum over the spin structure of the fermions. So although the fermions are not present in the low energy physics that you have to sum over the boundary conditions for the fermions.
Even though they're very heavy.
Yeah.
Okay.
The partition function has a sum, just like it has a sum over all the gauge configurations.
Right, it has a sum, but it's summing over things that have decoupled. The contribution of any excitation to the fermions is gone away.
No, but the boundary conditions you've got to sum over, right?
Right, you sum over the boundary conditions, but it doesn't affect the gauge field. But it doesn't affect your low energy ones.
Yeah, but you can show that the partition functions are the same.
There's a part which is, I see. I mean, the difference between one spin structure and another is suppressed in e to the power minus n.
Yeah. But you have to also see how it interacts with the boundary conditions coming from A.
So it affects the boundary conditions of the gauge fields. That's what
that's right. Yeah. And to keep it time, the way in which time reversal is implemented is very different in these two theories.
So the sum of the spin structures of the underlying UV theory gives you some effective boundary conditions in summing over the gauge field.
Yeah. I think so.
I see.
The thing is, when you say spin structure, you're assuming it's like an orientable manifold.
Okay.
But it's important to show it for non-orientable manifolds because this is time reversal symmetry, which is actually like a reflection on the time direction. So you need to actually glue together these. So one of the main ambiguities over here is whether this this duality holds for a single flavor or for example you can have three flavors of fermions. You have to have an odd number because you want p equal pi. But how do you know it's just a single flavor? And the main ambiguity is whether it's one or three. And that actually bothered us for a long time, and there's no simple way of settling that unless you do this, which is you see how these partition functions transform when you're on different manifolds.
And can you just say one word about why the spin structure of the fermion affects the boundary conditions of the gauge fields?
So we are also going to think of manifolds where there's a loose spin structure.
Okay. But just one example where, let's say the torus. On the torus, is there something interesting?
No.
What is the simplest manifold in which there's something?
So like RP4, for example.
That's about 5 feet.
But if you think about it, right, you want to actually think about, so if you ask how are these different theories, how do they differ? Let's say I have, this one. So if I have one Dirac fermion or two, how do those theories differ?
Okay.
So it turns out there's some topological invariant that can distinguish them.
Topological invariant in what?
So if you put them on different manifolds, okay, so let's think of a simpler case. If you have a topological phase which is protected by some symmetry, what you can do is you can insert fluxes of that symmetry and you can see how the partition function changes. The problem over here is the symmetry is actually time reversal symmetry. So what is the flux of time reversal symmetry? It's like you do time reversal for part of your space and not for the other part. Like you need to, so you have space and time, you want to twist the direction of time on one half but not the other half. So it's like you glue it, you cut the system into two, you twist one and then you glue it back. It's like a Mobius strip in space and time. And you want to evaluate the partition function of that. And when you do that, you realize that 1 and 3 are different. They give you different contributions to the partition function.
That's 1 and 3 on the composite fermions.
On this side, yeah.
You're worried.
You need this kind of time. You need this definition, side-to-side to get the distinction in 1 and 3.
You're worried that the composite fermion theory could be equal to 3.
Yes. Yeah.
That seems to violate some C theory.
If you want the strong form of the duality to hold, you need.
Anything you have some number of degrees of freedom in the UV of the 2ED3, and that's fewer than the degrees of freedom in 3 Dirac fermions.
Okay, that's the strong form, right? It is going to start with decoupled fields on the right-hand side. It's not actually clear to me that I think it was how many fermions is photon. In fact, that photon is not even like the Berkeley invariant. So.
No, but in the UV there's 4 degrees of freedom roughly.
But fermion and boson are different, right? Fermion and boson are different. But okay, that's yeah. I mean, that's looking only at the strong form, but for the weak form of the duality, it could have been like that. But let me give you the poor man's proof that I actually understand, we can refer you to this paper. But the only thing that the non-trivial fact that establishes is that it's the one-to-one mapping, not 1 to 3. That was the worry.
So just to say, so these two theories and the equivalences in the deep infrared, both are U1 theories. But this is a subtle thing about how the symmetries map and
That's right, yeah.
and so on. Okay, so and moreover, your point is that now if you have a boundary, then the zero modes are going to be related to these set, and that set is symmetry.
Yeah. I mean, for example, when you do this duality, the simple thing to do is you just look at this and you say, you always describe it in terms of monopole.
Yeah.
And that's this duality over here. You don't try to put it in all kinds of manifolds. At that level, you can establish this. But if you what you find is that you can omit the same argument with Cantley and that's what you need, this more complicated version which can actually test whether it's 1 or 3. Okay, so what we want to do is we want to draw a similar table, but with this theta equal to pi, and then you have fermionic charges. Okay, so let me just start with theta equal to 0 and fermions. The electric charge is a fermion. Okay, so then you have kind of consistent. Okay, so these are fermions. Okay, so if you have n, okay, so you have particles described by charge n and monopole charge n. And if you have monopole charge equal to 0, it's just the electrical charges. If you have an odd electric charge, that's a fermion. Okay, but now you can look at it in a more general space. And the statistics will turn out to be -1 to the n. Of course, that's this fact. But there's also a contribution coming from if you have a bound state of electric and magnetic particle, there's an additional contribution to this phase that's n times n. Okay, so if you work this out and sort of identify where the fermions are, for example, if when n is an odd number, this is always a boson, so all of these are bosons. But if n is an even number, then the odd ones are fermions. So these are the fermions in this pair. Okay, so now let me move to theta equal to pi. Okay, so all that happens when you go to some finite theta, you have this term. You can write out this term what it is. So it is theta over pi. It's just E dot D. Some normalization works. That's what this term is when you open it up. So what if I write this as this electric field as a minus of gradient of some potential, and I do integration by parts, what I find is that this phi couples to divergence of B. Okay, and so divergence of B is just the density of monopoles, 2 pi times the density of monopoles. So this phi times the monopole density, and the theta is pi. What I find is that there's a coupling between the potential and the monopole density. Okay, so in other words, the monopoles have acquired an additional charge of m over 2. Okay, so now the electrical charge is whatever I had before plus m over 2. So I can now describe it as q times m. Okay, but this electrical charge doesn't contribute to the statistics, so you still have this old relation, what the statistics are. You're just going to slide everything by this m over 2. Okay, so let's draw that. So again, you have it labeled by charge Q. M. Okay, so if M is 0, you had what you had before. You have this and this being the fermions. But now you have M equal to 1. So you're going to take this and slide it by a half. These things are going to sit over here now. Okay, and they're all bosons just like before. They're just being split up by a half. And now M equal to 2, then you slide everything by 1 unit. Okay, but then this fermion has come up over here. So this is one of the key. First, it transforms to itself. So there's something about the Kramer degeneracy of this object. This actually has a spin, and you can figure out where the Kramer degeneracy comes from. It comes from the fact that you combine these two to get this particle, and they're exchanged by time reversal symmetry. Okay, we won't go into that. Let's just look at the boson or fermion nature. And now you can equivalently describe all of this physics in terms of this fermion. You can say these are my particles. I can take those particles and put them in a band structure that gives me this theta equal to pi. And that should generate the same physics because I can just do this all in reverse. I can call this the electric charge. I'll find that the double monopole is fermion and you'll get the same thing. But now the difference is that if I apply time reversal, this particle will go into this one. Okay, and that's this duality. Okay, so we're almost done now. So what you can do now is we want to actually get these two surface states. Okay, so both of these have surface states. This one, is I want to think of this as the regular, the fermion, the one with short-range interactions, and I want to think of this as the non-trivial one. Okay, so how do you do that? So let's say you have a particle with like an electron. You have some electron, which is some fermion thing. It can combine with this object over here. So let's call this the particle psi. Okay, you can take this product, which is a boson, and you can condense this particle. Okay, it's just Higgsing. It's like a Higgs transition onto this U1B state. Okay, and when you do that, everything is all the photon is gone. All you're left with is this electronic excitation, and it gives you a phase of matter, which is just what's called the topological instate. Okay, there's something which has only short-range interactions, and there's a surface which has a blank. Okay, but then you can ask, in this language, what does it correspond to? But that's a highly non-trivial state. Okay, in this language, these are the electric particles. You took this theory which has these electric particles, you went and identified their double monopoles. You took double monopoles, stuck a fermion on it, and then you confine everything. Okay, so the bulk, again, you can show is completely confined. There's no low energy excitations. But it's a condensate of double monopoles. Okay, so you have a boundary. You have a double monopole condensate. It's stuck to an electron. But there's a condensate in the bulk. Outside, you can always think of the outside as being a Higgs space.
Condensate, you have some additional interaction that binds you.
Yeah. So it's you have some binding, and then you push it so the mass gap is small and it's a boson and condenses. So at the boundary between this condensate and just the electric charge condensate, you can combine this with the fermion again. Outside the theta is 0 actually, so this is a boson. You can just condense the electric charge. If you look at the boundary between these two, you have again a black cone, but this is coupled to a photon. Okay, and the reason is that your monopoles cannot freely tunnel between the outside and the inside. Okay, so everything got confined to the bulk, inside and outside, but at the surface there's still a photon. Okay, and this is just the right-hand side, which I now erased. Okay, and it has this feature that because it's a double monopole condensate, I cannot tunnel a single monopole into the bulk. Okay, that would completely change the bulk. I can tunnel in a double monopole into the bulk, but then I have to grab an electron to enter this condensate. So the double monopole tunneling operator is just the electron, which is what we said before. The electron insertion is just the double monopole operator. Okay, so that's like how you argue for this.
So this argument is an argument for the weak form of the
weak form, which is the only thing you can do.
weak form was again, sorry, what was the weak form? Just
That they describe any phase which I describe in terms of these variables is some way to describe in terms of other ones. But I can't tell you a specific map with coefficients for. Strong form posits that there is a certain map, in case one point is mapped. Free theory on the left hand side, low energies, and QED3 defined in this precise sense that it's decoupling at some cutoff and then you,
So the strong form is currently just a conjecture.
yeah.
But why do you need the conjecture? I mean,
It's just, it sounds persuasive. It might actually be true. That's something that is, usually, normally people would say QED3 is not even stable in 3 dimensions.
okay.
But it may actually be stable only in maybe a few years. It's more like
But the weak form is enough to establish the connection between, let's say, the monopole system and the topological insulators, which is
that's just
from a conventional viewpoint quite remarkable.
Yeah.
And locally there's the whole Dirac picture,
Exactly.
non-mathematical, purely physical. And explains why the very phase is pi.
Yeah.
So, if you make a junction between the normal phase and the double monopole, can you have some equivalent of Andre reflection for the monopoles, the monopole current going coming back as a minus A current and then a positive current? And if so, what would that give you any experimental signal?
Well, it should not. I mean, it should. It's just a way of defining a very conventional phase, but a new surface state. And the question is this surface state really a different phase from the usual Dirac surface state that you have in distance element? Or is it just the same phase in some fancy variables?
I mean, right now it seems that bed should be the same phase, right? Or
That's the strong form of the duality.
Right.
Saying that
all
the class is just
all right, now I get you why okay, I do want the strong form. Okay, all right, now I understand.
Suppose you assume you have your strong form, the duality. Now I change the right hand side by adding a Chern-Simons. I add a Chern-Simons term for the gauge field of the right hand side.
what strength? What level?
For arbitrary integer.
Okay.
Would you be able to, from your strong form, derive what you expect the left hand side to do in that? If you did that? Or maybe, I don't know. For Chern-Simons for your middle.
Sure, yeah. So, I mean, once you add that, you break time reversal. So at least as a phase, I would also get a mass term for the Dirac. So you have k shifted to k plus half, right? Plus or minus half. So that is some sort of topological order. That is so let me just look at the response for a second. It's the response would be, it's not like a fractional polynomial state. Right? Let me just integrate out. So let me just do k plus half. Right? So this is definitely some 2k+1. I wonder if it's just, so in broken Tandler-Wilson symmetry, we do that. So maybe it's just the, so on the left-hand side, you've broken to particle-Wilson symmetry. And maybe you just filled up some
number of levels.
Maybe just that. Because at lower edges, there's no, you gapped out everything. Right? The real question is it topologically ordered or not?
Why have you gapped out your composite fermions at lower
Okay,
edges?
you could tune them to be gapless.
Yeah, let's try that.
Typically, there would be. So that is like a transition between two states, right?
That's what you were describing in your CFT.
Yeah, he was saying that symmetry fixed you.
Yeah, there is symmetry.
But let's say I tune.
I see.
Okay.
Okay, then you know what? Let me say what I'm getting at. Your right hand side looks like the RG, like the IR limit of a nice Lagrangian theory. But you've got to take this very strong coupling limit because the F square goes away and that's very strong coupling. But I was wondering whether your duality might be one point in a series of dualities where there's a Lagrangian description of the IR physics. Where the gauge field is not completely strongly coupled, but controlled by a Chern-Simons.
So you're saying also on the left-hand side you want the Chern-Simons?
I don't know, whatever you get on the left.
Yeah, I mean, the first order of business would be to identify what that phase is, right? When you actually have a master. And then you flip the sign of the master and identify these two phases. If I correctly identified it as an integer polynomial state with large number of lambda levels fixed, filled, then it's a question of whether you have 2k plus 1 or 2k minus 1, all index. So it's some transition between them.
I see.
It may be like multiple. It sounds like it's a weird transition because so it's very key to get this coefficient right, which I'm not sure about. But it may be you are changing many lambda levels. It could be so a transition between the lambda level n and n plus 1 is a single Dirac fermion. This could be like several Dirac fermions. I should get the answer I have for k equals 0, right? That's at k equals 0. But you're adding this. Yeah, so k equals 0 is just like not adding anything. It's almost like it doesn't depend on k. Okay, that's something to.
So, Ashvin, one comment. So this is very beautiful and quite compelling, but it seems that very little of it will survive disorder, right?
That's usually the case, yeah.
So I think it's, well, I mean, I think theoretically, of course, it's very compelling, but it's probably worth thinking.
Yes. Yeah.
Is there any feature that will be the survive disorder because you have such a complete theory?
Well, people use this Vishwanath duality to talk about this on superconductors. So it's just different variables if you like to describe the same physics. And the nice thing sometimes is that things that are hard in the usual variables are easy.
Yeah.
So it makes predictions. Dirac nature of fermions, new kind of topological order at the half and lambda level.
Right, beautiful.
More questions?
On that one, shouldn't the topological aspect be at least robust to disorder? Or do you think
Yeah.
the whole thing?
Yeah. To be
Questions? Okay, that was a fantastic talk. Thank you.